So we only have probably about 20 minutes for questions. So let me bring that up again. Option Y on Mac or Alt Y on Windows for questions for Fabrizio. And let me see, Robert DBS, go ahead, sir. Oh, I'm sorry. I'll allow participants to unmute themselves. There we go. Asked to unmute.
Okay, thanks.
Yes, sir.
You know, basically, I'd like to get your reaction on some results from quantum field theory. There have been a number of papers that have been published on this, where it's about Casimir wedges, and they allegedly produce torque forces. And using a little bit of high school vector analysis, you get this anomalous force in the direction of the wedge angle bisector. So I'd be interested in your reaction on that.
So, I mean, I always react to, and again, Robert, if you would like to email me or email Tim with references, I would like to see the references. So
I can tell you, I mean, 1979, there's a paper by Deutsch and Candalis.
Right.
And
so on the wedge, the calculation of Casimir forces with wedges, again, very complicated because it's a non-standard geometry. There is no doubt that there are torques in that case. That is very interesting and technologically applicable. But I want to be careful about the implications. So torques, yes. But when we talk about the non-conservation of momentum, I get more suspicious. So I would like to see whether Candelas claims non-conservation of momentum, because I think that they claim the torque, which is a correct statement. But whether you can extract momentum from the quantum field, I don't know if they've done that. So because you talk about application of vector calculus, you know, at the high school level, I would like to make sure that I mean,
I have corresponded with Ivor Breivik, rather. He's another author.
Yeah, Breivik, yeah, sure.
Yeah, and I was suspicious myself. You know, I said, is there some vector in the R direction that would cancel out this anomalous force? And he told me, no, there's no vector in the R direction. In fact, he agreed that there is this anomalous force in the direction of the angle bisector. And he says there's no contradiction, conservation of momentum if you keep the entire system in mind.
Right. So, and I agree. So if we keep the entire system in mind, then there is no violation. So what that means is that you can actuate the devices that way by introducing this torque. I have no doubt about it. I become concerned when we trust the models too much, because then you can imagine making a machine that harvests energy from this object that is spinning out of control. So I want to make sure that we don't, because then we build things on false conclusions, you know. So, but I agree with Breivik on that issue.
Okay. Well, I went a little further. I actually proposed an atomic force microscope experiment to see if we could see these lateral forces. And I'm in the process of putting together such an experiment along with a collaborator in Germany.
Yeah, and is probably I know the collaborator in Germany also, but
I don't. Yeah.
Yeah. So
I don't want to say his name.
No, that's okay. Probably a good friend, but so what I'm saying, yes, but what I'm saying is that I think that he and I have discussed this issue, and I think that the AFM allows exploration of Casimir forces in non-standard geometries, and I think that that's an open field for the AFM. Of course, the challenge is the fabrication of the structures themselves. You know, that's the issue.
Well, we've gotten beyond the structures. That now it's actually putting together an apparatus that can unambiguously disentangle the normal forces from the lateral forces. And this is where we are right now.
I'm impatient to see this publication.
Okay.
Good luck.
Thank you very much.
Sure, good luck.
And thank you as well, Robert. Okay, let me go to Michael Boyd next, sir.
Hello, sir.
Hello.
I'm curious. I've heard when I hear about the Casimir force, a lot of times I hear mentioned the vacuum energy. What would you disentangle that for me, please?
Yeah, of course. I mean, this actually goes back to Casimir himself, because Casimir, I showed the slide before in which Casimir said, let's calculate the energy due to the quantum vacuum oscillations between the two plates. And I don't know if Tim wants me to go back to the slide or if I should just wave my hands. What should I do with him, Tim?
Oh, if you want, you can put the slide back up.
Okay.
We have a few minutes left, so.
Okay, I'm going fast. So I want to answer the gentleman in the way that is, did you get the thing back?
Yep. It looks like it's perfect.
Okay, so I'm going to go to it. Okay, let me go back to that slide in particular. And I mean, this is fine. So basically what Casimir said is we got the vacuum, what you call the vacuum, doesn't exist in quantum electrodynamics because of the uncertainty principle. So whereas we teach in school that if in a area, in a region of space without charges and currents, the field is empty of energy, in quantum electrodynamics, you cannot say that simply for the reason that the uncertainty principle says that you cannot have all components of the electromagnetic field zero at the same time with infinite accuracy. Consequently, the energy of the electromagnetic field is not zero at any given point. And this is one of the great mysteries that remain, in the sense that if you take quantum electrodynamics at face value, the energy of the electromagnetic field should be infinite. Or as Weinberg said once, would be like, 10 to the 122nd power or something crazy like that. But it isn't, obviously. So we don't know what's going on there, but what we do know is that there is some energy in the vacuum of space. And the only thing that Casimir did was to calculate not that energy, because we don't know what that energy is, but the energy change. So because forces are the derivative of energy with respect to position with a minus sign in front, even if you don't know what the actual energy is, and you take just the derivative of this thing that we don't know, you can get the force correctly. So that's what I'm trying to do for you. I'm trying to tell you that the reason that you hear the word Casimir force and vacuum at the same time is that one way to explain the existence of these forces is that you need to think of the vacuum of space as not empty, not vacuum, but there is energy there.
But don't reflections of the surfaces cause different oscillations?
Yeah, so the presence of the boundaries, as in this slide.
Like projection causes, see, even the vectoring right here, the right side, my right, has a darker color than lighter. So light reflections changes. So the frequency would change. It just depends on,
the frequency, right.
Angle.
So the frequency, the calculation that Casimir did, if that's what we're talking about.
Yeah, because there's light reflections, so the frequency goes up.
Well,
right.
and Lulu, if it's okay, let me have you wait until.
Thank you.
That's so I don't
follow up on that question about the vacuum energy. So
yes.
do you know who Dr. Hal Puthoff is? He's he's done some publications on this Casimir vacuum energy too. And I asked him this question. My background is in infrared and semiconductor physics, that kind of stuff. And a semiconductor has what's called a band gap. You understand what?
Yeah.
So my question is this let's call it a field, this Casimir field, does it have a band gap? like a semiconductor.
So if you are talking about the band gap of the two slabs, if you can imagine the two slabs made of a semiconductor, then the optical properties of the slabs do affect the Casimir force greatly.
Well, no, I'm actually talking about the region in between the two
No,
slabs.
no. So no, so if the vacuum is a vacuum, I mean, of course you can put water in the middle, you can put alcohol in the middle, okay, you can put anything you want in the middle. But if the gap between the two is empty of any other substance, then the frequencies are determined only by the boundary conditions between these two plates. Just what they teach you in school, you know, because you know electrodynamics, so you know that the electric field at the two boundaries will vanish, to give you an example. So that determines which kind of oscillations you can have due to the vibrations of the electromagnetic field that are caused by the uncertainty principle. On the outside of the region between the two plates, there are no such constraints. So on the outside, all vibrations are possible. In between the plates, only some are possible. I would like to stress that this doesn't explain why the force is attractive, because in reality, technically speaking, there is an infinite number of vibrations possible both inside and outside. So you need to be careful.
It could be repulsive too.
It's possible. It's possible. Yeah,
Yeah.
it is possible.
Well,
Yeah.
well, and Michael, yeah, if it's okay, I have some more.
My questions. I appreciate it.
And thank you, Michael. Sorry, I'm trying to rush because we're getting towards the top of the hour. So let me see. So next, actually, I had one in chat. Monomorph could has he'd asked, please ask Fabrizio what he thinks of Sonny White's recent work with Casimir cavities, and if he thinks there's any potential for using the Casimir effect for reactions propulsion.
So I know that I have been cited in the context of that research. I don't know why, though. I mean, what I think is that to the very least, the jury is still out on whether Sonny White has got something or not. But typically when people don't know where something is coming from, they say it's got to be the quantum vacuum. So my fallback position when people say that is, if the vacuum were not quantized, if we had a completely classical electromagnetic field, would you still have this effect? So if the answer is no, I don't trust it. So that's my opinion right now. But I understand that maybe I am being too conservative. So I would like to see the final data on Sonny White's device, though, because that's still, I don't think that we have seen the end of that. So.
Okay, well, thank you. And then let me go back to Lulu, if it's okay. Lulu, are you still, you're still on, right? I'm not sure. Okay, yes. And then you had a question a moment ago, and could I ask you to turn your camera on, if that's okay?
It's on. I turned it on.
Oh, okay.
Yeah. Hello.
Hi.
Hello.
I had a question. Well, a couple of questions, but with wave frequency, it doesn't, you know, depend if the particle that it's touching on one side, when it bounces back to the other place where the particle's touching, wouldn't those two things for it to create a harmonic would have to be, you know, like 100% of a pure element in order for that to be perfect? Otherwise, things are, you know, you don't know what
right. So yeah, so but it is in this case, because in this calculation that I have on the slide right now, if it's still visible, which is the proper, this is the calculation that the Casimir did. These are two perfect reflectors. So it is exactly what you're asking for.
Okay. So, you know, like, and then you had the angle of the arrows on the two slabs from that side, all coming vectoring down, or it's plateauing, but you still have a wave propagation, even if it's at zero. That's the only really one that's going forward.
So you know? and what you see in the calculations here, which is not friendly, but it's the sum over all of those. So it's not just one of them; it's all the possible directions in all possible times forever. So it's a calculation done from 0 to infinity, from 0 to infinity, from 0 to infinity. That means that we are calculating all possible directions for these arrows to go. because all,
errors. Okay, so you're calculating for errors. You're not calculating for possibilities, like, you know, like.
I think he said arrows. I think he said arrows.
Arrow as in this thing here. Arrow, the direction of the motion. Yes. No, there is no uncertainty. We haven't even talked here yet about the noise of the Casimir force, which will be the uncertainty on it. That's a very, very small number. So right now we're talking about a static Casimir force.
Yeah. Well, let me, Lulu, thank you. Let me go to Bernie next, really quickly, and then I'll go to Will after that, and we're probably out of time.
Thank you.
Hi, thank you so much. That was an amazing presentation, Dr. I hope your students call you Dr. Fab, because that was fab.
No, but it's okay. Fabrizio's fine, and it's the same for you. Thank you.
Thank you, Fabrizio. Very fascinating. Are you familiar with Nassim Haramine's work at all with the Casimir effect, and how he ties it in with Coulomb's law and not quantizing, but tying it into the holographic memory of the structure of space-time?
Can you repeat the name? I didn't grasp the name of the person.
Nassim Haramine. He's an Iranian Canadian, but now he runs the Resonance Academy out of Hawaii.
I cannot say I'm familiar with what he has done. If you would like to send me the reference, I would be happy to give Tim a response on that.
Yeah. Absolutely. His main paper that would be relevant is the Schwarzschild proton.
Okay.
Thank you.
So much.
Yeah, thank you.
That was fascinating. Sorry, one last quick question or comment was how you noticed that shape when you're showing your very first pictures of what looked of that experiment from the past, and how it resembled to me all the alchemy experiments of stuff.
This one?
Yeah, well, at both of those. And just quickly to tie in is that I've been reading a lot of Sir Isaac Newton's alchemy writings, and then in my own experiments reproducing some of them. And you started out talking about Isaac Newton, and a lot of his theory that was missing is in those writings. So gather of them.
Okay, and Bernie, thank you, sir.
Thank you.
So let me apologize. I'm rushing here. I want to get to Will, and then I think that we've wrapped things up. So Will, go for it, sir.
So in Lulu's question, you mentioned that frequency was important, but then in Michael Boyd's question, you mentioned that whatever the material between the plates was not important. But my understanding was that one of the reasons of going into to use the vacuum was because dielectric constant is important. So which is true here?
Yeah, it is true. Good point. So we're talking about two different things. That's why, unfortunately, the conversation has been very long today. But in all these discussions, we have talked about the Casimir force. But this is the
possibilities. You guys were seeing exclusions. That was the difference.
Yeah. Let's if we're okay, let's wrap this one up, and then we need to move on to our next speaker.
So what I'm trying to say is simply that in the Lifshitz theory, you deal with the dependence of the electric properties on frequency. So in the imperfect materials, in the real materials, you use the Lifshitz theory. And so then you have the dependence on frequency in the dielectric function. In the ideal case, however, epsilon goes to infinity. And so at that point, it doesn't matter. So be careful when you're talking about the Casimir force. Are you talking about the ideal case or the real case, in which case you need to use the Lifshitz theory?
You explained like quantizing packets between platelets.
Lulu, please.
And sending them to Centauri.
Lulu, I'm sorry, I have to mute you. We're almost out of time. Okay, I'm sorry. Fabrizio, could you finish, sir?
Oh, you know, what I'm saying is simply that I think that I agree with the last gentleman who spoke that generally speaking, the properties of the material as a function of frequency are crucial. However, they are not crucial in the case of the Casimir effect proper, because in that case, we have taken the reflectivity to be infinity, to be equal to 1, sorry. So in that case, epsilon is equal to infinity, and in that case, it doesn't matter. It's a property of the quantum vacuum and nothing else. So so there is no contradiction.
Oh, okay. Sir, thank you very, very much.
Thank you.
Okay, and we're out of time. I should apologize. Lulu, I apologize for cutting you off. And so let me do this. Let me put this back on gallery mode, and I'm going to stop your screen sharing.
Thank you.
Yeah, and again, everyone, please give a
Thank
giant
you.
applause for Dr. Fabrizio Pinto. Sir, thank you very much. And
Thank
I
you.
apologize for rushing through the question and answer. This was a wonderful presentation, incredibly educational.
The fault is all mine, Tim. I kept talking. So
Oh, no, not at all. Not at all. It's wonderful, wonderful content. Wonderful content.
Thank you.
Okay, so
luck.
let me do this. So next